for paper purposes, I'll just show like 3 digits, 3D0, 3C8, 3C0, and on it goes. Okay, when a program is running, it has a set of space set aside for it called the activation record. The purpose of the activation record is to provide storage for all the local variables of that running function. Here are things we know. The back end is on the boundary always, and if it's an active activation record, if it's really active and because its function is running, then RBP holds that address of the back end. While it's running, the front end is also on the boundary, and RSP holds that address of that front end quad word. Okay. At the moment that a new function is called, one more quad word is added. It's a push. One quad word is added here, and therefore RSP moves ahead with it. RSP. I can't make that. Okay. And that closes off the old activation record while the front end is off the boundary. And that's the end of it. It's major boundary here. Major people will just there's a separation between the old activation record and the start of the new one. Okay. But all the time that function is executing, both the front and the back are on the boundary. The back end is on and the front is on. At the moment it goes inactive, this extra quad word is pushed, and then it's off the boundary, like that picture shows. But the new activation record then starts on the boundary. Here it starts new. It's on the boundary. And the pointer to that back end, new back end, is RBP. If it's C++, C++ adds up all the storage and all the locally declared variables and finds out how many bytes are needed, and it places RSP down here so that the right amount of storage has been declared. Sometimes there's garbage spaces. For example, if you had an array of 5 items, it will round it up to 6 so as to maintain starts on even boundaries. But it does calculate what's needed and places RSP here. And then this is the new activation record that's active while the subprogram is running. One more thing, remember that when this extra quad word is added in, it holds RIP. Okay. This one doesn't have it if it's active. It doesn't have that extra quad word at the end of it. Okay. So we're going to learn GDB, and see this in live action. Okay, let me check, see if there's anything. Okay, you're welcome. Everyone's got that picture in your mind. And if the second function calls a third one, another AR will be formed further down here, next AR. And when they disappear, because the function is returning control to its caller, this disappears, in the sense that RSP backs up to the other one, and it doesn't indicate this even existed. Okay. I think we'll start out and see how far we can go. Once in a while, I record something and then we'll share it on this yellow page. Okay, so here I'm going to start a program. It's not the same one as last class meeting, but it's kind of similar. Let me search to where it is. Let's see. Okay, let's move this where. And I'll share the screen with you. Share screen. We're going to get the whole desktop. Whole thing is here. Okay. Here's the files. Let's open all three. Well, really, fortunately, that's just all comments. We're going to quickly go past all that. And that's the called function. Where's the driver? This is okay. So when the program starts, it's a runtime system, part of the operating system itself. It's going to count how much storage is needed by adding all of these together. A double is 8 bytes, and there are 1, 2, 3 numbers in here. 8 times 3 is 24 bytes. A long is 8 bytes. Again, there's 3 of them. There's another 24. That adds up to 48 bytes. A char is a single byte. And there's 5 of those. So you add in 5. These, I thought they were going to be, it turns out the machine uses 32 bits, 4 bytes for each one of these true falses. We're going to see that happen in a moment. Okay, and so it keeps adding, what did I say, 4 bytes, 4 bytes, 4 bytes, 4 bytes, 4 bytes, and then doubles are 8 bytes for each number, 8, 8, and 8, and 8, and 8. And so I don't think any more is declared below that. And so all that adds up, and that creates new storage on the stack, and that new storage is called the activation record belonging to main. This is main here. And you know what? One line is out of order. This is a prompt to input 3 floats. Yeah, let's cut it and cut it here, and put it here. It's just above the scan that's going to get the 3 floats. Okay. So, you know, just as an aid to reading float numbers, keep in mind that if the exponent is 3FF and everything else is 0, the number is 1.0. If the exponent is 400, the number and everything else is 0, the number you're working with is a 2.0. If the exponent is 401, that coincides with 4.0. If the exponent is 402, that the numbers double. That corresponds with what did that last say? Let me stop this. Just one minute here. We're thinking of hex numbers. 3FF and everything else is 0. That's 1.0. If this goes up by 1, everything else is 0. Then this is 2.0. If this is everything else is 0, that's 4.0. 402, 0, 0, 8.0. Okay, and it goes on that way. 403 will be 16.0. Now, suppose I said, well, what do you think 6.0 is? 6.0, and this is 4.0 up here. We know what it is, 401, 000, That's 4.0, and 4.402000 is 8.0. So 6 is halfway between them. It would be between 401 and 402. If you had a 1 bit right next to it, it would be 401. And then you want to split this difference. That means you would have a 1 and 000 in bits. And a 1 followed by 000 is 8. And it works that way. I split the difference halfway between them, and then I have a 6.0. Yeah. We use this to sort of read hex numbers when you're using GDB. 40, let's see the space there. 403, 0000000. That's 16.0. And what would it be halfway between? It would be 12.0. Halfway between these two would be an 8 in this position. And that would be 12.0. Got it? Okay. And we could split the difference between these two and find what the 14.0 is. In fact, you can see it already coming forward too. Between 8 and 16, it halfway is at 12. That would be a C. And so that would be 14.0. You can't do it with very complicated numbers, but for simple numbers, that's, you can almost do it in your brain. Okay, let's go back to the program we're running. Share. Didn't quite click the last piece of the puzzle. Okay. So we're going to see these numbers, and here's a defect. I mean, it's part of GDB. Is if GDB is going to show you a float number that's actually 6.0, it doesn't show us the 0.0. It will just show us 6, and it looks like an integer. So you have to get your mind accustomed to this. If GDB is showing you some whatever, 15.0, it's just going to show you integer 15, and you have to figure it out that, that was actually a float 15 in IEEE format. Okay, so I attach these little numbers on the end so that GDB would be forced to show me more than just say the front digit 2 or the front digit 4. That's what's going on there. And is there anything else? Let's look at discriminant. Discriminant is really small stuff. What is this? Name of this is discriminant CPP. Can I do some? I'm having trouble with. I want to do something with W. Let's just throw in. Oh, I'll have to have. I do have IOStream. Can I print F before we start? PRINTF parentheses quote long is right again percent LD. My cursor is jumping terribly. I'll try again. Percent LD quotes W. Now I think it looks okay. I think so. Control, save it. Okay, we only have two small variables in here, a D and a W. I think that's going to be 2 quad words, but I had trouble proving it last hour, but we'll see what happens. Okay. And what's the last part of this? You remember this from Tuesday. You have to enhance the bash file by adding -G on the end of these. This one's been commented out. There's no assembly today. This is a -G and a -G and a hyphen. And there's a GDB down here. Remember that part of it. This is the executable file that was created a few steps earlier. Okay, the bash file is the same one, except you add the -G on it. That's, why does it save? Okay, gotta click on save here, save that one. And let's start a run. Okay, here's the place, get a terminal. Terminal looks okay. Okay. Okay, let's run this rg.sh. And I have a bunch of warnings because this is not a real program that solves anything. This was a program created artificially just to study GDB. Okay, so the warnings don't mean anything. They say I didn't use the variable that I declared. We don't care. All right, so here is the first, when you run it, you'll get a bunch of garbage here about, I don't know, copyrights from the Free Software Foundation and so on. But here, as a rule of thumb, you want to set some breaks first. Okay, so what do we have to break on? Good question. Okay, where's my, did I close that file? There it is. So it's common that you break on the name of a function. There's the name discrim. And the other function was driver here. I'm sorry. Here's the name of this function, main. And discrim is in a different file. Here it is in its own file. There's the name of a function. So we have two names, and let's pick one line number. In here, enum is a weird one, so let's pick line 59. So it's main, discrim, and 59. Okay. Break, M-A-I-N. Break, D-I-S-C-R-I-M. Break 59. And check and see if they're all there. It looks like it. It looks like it. All three breaks exist. Okay, so let's run the program, and it will run automatically to the first break place. But I put the break, where'd it go? Where'd it go? Here. Okay, I put the break very early at main itself. Main is not an executing statement, but you watch, it will stop on the line right after it when this runs. R is for run, and it started the program. It had a breakpoint. It tells us breakpoint number 1 is on main, and it's about ready to execute line 54, which is to output this message. Okay, there are several ways to advance the execution. The letter N, the letter S, the letter C, and then two variations. NI is called get information about the next statement. S stands for step, and SI means get information about the next step. And lowercase c stands for continuation. That continuation means execute continuously until you reach the next breakpoint and then stop. All right, so if I say NI, it's all lowercase, NI. Okay, it tells me this is what's going to happen next. I'm going to, did I do that right? Output the message welcome. Let's actually do it now with an ordinary N. It outputs the message in dark black font, and it shows me line 56. I'm going to execute that one next. But by executing a declaration, and that means it's going to put those numbers into the activation record. That's the execution of a declaration. Okay, before we do that, let's investigate and find the activation record. So there are two commands, P and X, that show you information. P shows you direct information directly out of the variable or directly out of a register. If you start with the X command, it tries to dereference whatever you have and show you what it points to. All that. So here is, let's show those two cases. P/X $RSP. That's direct. It'll show us exactly what's inside of RSP. That's it. That's the address at the front end of the activation record. If I use X/, should I do? I'm going to ask for 1. When you dereference, it doesn't know how many quad words you want. So I'm saying, give me 1 quad word in hex format, and G is there's letters that you thought they would use a Q, but they didn't. They use a G to represent quad words. Okay, now we use the same parameter, RSP. And what we get is the value stored at the top of the stack. This is the address at the top of the stack. So the P command is direct. It gives us exactly what the variable object, like RSP, is holding. This one over here is the address. It says in blue, that's the address, and I've dereferenced it to show you what is stored at that address. Got it. And let me see. There's a slight deviation. Suppose you didn't want to break it up into, let's try, that's the one less than that. I think it's H or W. Let's try H. H. And then we go with 2 of them. This is supposed to break the contents up in half. Okay. Yeah, it's right. Okay, so it actually, that's 16 digits. It only gave us okay, you can read it here. So it gave us that piece of it, which is from here, and then it gave the one right next to it. But my mistake was I should have asked for 4 pieces. 4. I haven't hit there it is. Okay, so reading in Little Indian, where you come over here first, this is the first piece of it, and then this is the next piece of it, and then 7FF is the third word, and then the last word, 4 hex digits, is 000. So a word is 4 hex digits, and a double is 8 hex digits, and a quad is 16 hex digits. We now know that the letter H leads to words. I'll show you one other one. Let's do that with W. RSP. So back here, if you cut this in half, it would take you to about there. And that's the first one. And then you take the remaining half in Little Indian style, and then that's that number. And then we don't know the second quad word inside of the stack, inside of the activation record. It would be this one is the first half of the quad word, and this is the other half of the quad word. That's kind of a strange thing. How can, let's verify it. So X, we want, let's say, take the first three off the top front end. That's quad words, $sign, RSP. Okay. So this is the front end of the activation record. This is the very front end. This is the next in quad word after that. And this is the further in quad word after that. And up here, it was breaking it up in halves. That's half of the first quad word. And then this is the second half, reading it in Little Indian. And then this is the first half of the second quad word, right there. And then this is the next half of that same quad word here. And I didn't get down to this other piece because I'd need to ask for more groups. This 4 would have to be 6 or 8 or 10 or something. Okay, so how did we get here? Before creating the array named R, I wanted to investigate some part of where the activation record is. So here in summary, here's what we know. P/X $sign RSP. That's not a $sign. $sign RSP. And also RBP. BP. And RBP is bigger. If you look at it, this E is smaller than this F. Okay. That and everything in between is the activation record. And then I gave you this formula last time, P/D parentheses $sign RBP minus $sign RSP parentheses divide by 8 bytes in a quad word plus 1. And it says we have 21 quad words in the activation record. I'm going to stretch it a little more. So now, knowing that there's 21 quad words there, we can see all 21 of them. No, I'm going to dereference what's in the RSP. So it's X/21 of them. I want to see them in hex numbers, and they're quad words, and they start at RSP. And let's see, this is the front end of that activation record that belongs to main. And this is the second quad word after the front end. And this is the third quad word after that. And so it reads across the table here. You read the left side column first for a quad word, and then you go over here and read this side for a quad word. And back to here, and then across. And the last one is here. That's the back end of the activation record belonging to main. Sometimes I said it had all zeros, but sometimes it does have a 1 there. I don't know why, but it marks the end. There's nothing after that as far as running this program is concerned. Okay, so now what was the next instruction is this one, create R. Where is it going to put R? Let's find out. P/X ampersand R. Machine says R has been allocated to DEF0. DEF0. Okay. And R is going to have 3 numbers, 4.5, 5.8, and a 10. Okay. And it's going to be right in that place that was formerly highlighted. F0 right here. Let's do the instruction and find out. Press N for next. Okay, it's done the job. Let's check. It was supposed to be in F0. Well, here's, did I say that right? DEF0, that's right. Here's where it was before, and here's what it is now. And you can look at it with your eyes and see my exponent is 401. 401 is a 4.0, and this one is just a little bit higher than 4.0. So sure enough, it's a 4.5. Yeah, got it right. Here's a 4.1, and this one's a considerable more higher. That's a 5.8. And this one, the exponent is 402. On the chart I was showing you 10 minutes ago, 402 corresponds to 8.0, but it's got an extra 4 here. So yeah, it's probably a 10. And so there's our, there's the array, that much. Okay. It is storing, that's a static array. It's not dynamic. It's a static array, and all of it is placed into the activation record, and the little r becomes synonymous with this address number over here, this address. Little r, we can say, is that the name little r doesn't go into compiled code, but that number will go into compiled code every time little r is referenced in source code. Okay, so what's our next one? It says the next one is going to be this array, static array. Little s is a name for the address where it starts. Let's find out what that address is. P/X ampersand S. DF10, DF110, DF10. It is right here. Okay. That's inside the activation record. And right now, I think that's all electronic garbage. But we're going to execute the next statement. And we'll put this in there and we'll see where it is. So next to execute is declare S. Let's actually execute that. Okay, can we find S? What was the address of S? Address is F10. Here is F1. Where are you? F10, right here. F10, and it's now changed to be 64. 64 is 6 times 16, that's 96, plus 4 more is 100, and sure enough, that's exactly what the first number is. The next number is 1024. What is that? Over here, 400. That means 4 times 16 squared. 16 squared is 256 times 4. That's 1024. It's just perfectly right on the nose. 1024 is right there. And -1, oh, that's our favorite. -1 is right here. Just what you'd expect. In 2's complement, -1 is a whole lot of S. Okay, so it's working. It does what the theory says it's supposed to do. Let's see what's going to execute next. We're going to declare another array, and these are 1-byte numbers. They are 8 bits, 1 byte. Your numbers can range from -128 up through +127. So all these numbers in the array are within range. Okay, what do you think it's going to do with all that? Let's find out where it's going to place it. P/X ampersand, where's the ampersand? Ampersand U. Oh, that's really strange. DF53. Okay, here's DF50, but 50 is over here. That's byte 50, byte 51, byte 52, byte 53, because of the little Indian part. So we read it. It's going to put the 33 right there. What is 33? I think it's 21. 21 means 2 times 16, which is 32, plus 1. And then whatever 52 is, and whatever 64 is. But it's going to put a 21 right there, and then right next to it be some other nearby numbers. So let's actually do it. Execute that statement. Go back and look at the stack. Look at the activation record. Sure enough, there's your 21. See how nice that is? And 34 means 3 times 16, 48, plus 4 is 52. And that's a 52. Okay. And we're going to call the function in a moment. What is NI here? NI. That's going to make a lot of ones and zeros. You know, this is a funny thing. I thought this was going to make 1 and 0 side by side, but it doesn't. It takes 4 bytes to store a single 1 for true, and another 4 bytes to store 1 for true, and another 4 bytes to store 0 for false. And so you'll see it happen. What's the address of T? P/X ampersand T. It's at F30. And it's going to be up here. Okay, you ready? So let's make it here. F30. Okay, reading in Little Indian style, there's a true, and then there's a true, and then it continues over here. Oh, I'm sorry. Then here's a false halfway, and then there's another false. So it shows true, true, false, false. And that's right. Then it continues here. Here's a true, and then there's a false. And that follows the pattern up above here, true and a false. And then it ends up with 2 trues, true and true. Yeah. Okay. All right, let's, I haven't looked to see if any questions. Let me get some things. My chat messages are going. Okay, you're okay. All right, no. Make a catalog of GDB commands that, especially that you could use during the final exam. You want easy access to find all the commands you really want. I'm gonna speed it up. Next. So it's declaring variables. Let's investigate one of them. Say D. D, where are you? P/X ampersand D. It says I'm stored at this location. Is it inside the activation record? E8. Well, here's E0. And if you counted E0, 1, 2, you go out here to E7, and then E8 would be here. Did I do that right? I don't know if I can. Oh, D is at E8. I think it's at F0. What is F? Oh, no. No, what am I? Okay, for class, I'm really doing this dumb. Those are doubles. Type double is 4 bytes. That's so I should count again. D is at E8. E0 and E. So this is halfway between. E0 and F0. This is, I don't know where the middle point is. It doesn't look right. It's a double. It's not a quad word. It's, no, you see, you want to see what I did? I didn't actually execute the D1. Let's execute it. Okay, where's D? D is at E8. E8. Okay. E0 is a quad word. It's type double. E0 is here. E8 is here. Okay. 402. That's that table I showed you before 20 minutes ago. That corresponds to 8.0. But this number is slightly larger, so it's 8.0 plus some trailing stuff in the mantissa, real small. Okay. What was, I had a hard time finding that one. Let me find C. So P slash X ampersand C. It's at E0 and it's a quad word. Double in C++ is a quad word. E0. It's this whole thing. Okay. 401 corresponds to 4.0. This is 4.0 plus a small mantissa extra. Yeah, it's this guy back here. Okay. They're all in the activation. Let's go on. Any questions? NI, what's going to execute next? There's going to be a message. There's the message. What's coming is a scanf. Now it's waiting for those three numbers, 10.1 space, 12.2 space, 13.8. There's three numbers. It read them in. It's going to tell us in the next command what numbers were read in. There are the numbers that were just read in. Now there's a warning that it's going to call the discriminant. That's an N. And here it says we're going to call this discriminant function and pass those three numbers to it. Now, if I press N, I will not see the inside of discriminant. So I have to use an S. Okay, so we press S. We're inside of the discriminant function. The first thing it's going to do, line 53, is declare W and set it equal to -1. Here are the three passed in values. It's reminding us. The three values passed in are right there. Okay, so we're inside that. Let's do one more command next. The next says I'm going to compute this equation. It's the discriminant of a quadratic. And so let's actually compute that. And then it says we're going to tell you what W is. That's going to output a -1. But before we go there, let's verify what is this activation record. So we have to find out how many quad words in there. And I did this program early in the middle of this morning, and it has a strange output here that I don't understand, but let's do it again. P/D, parentheses, $, RBP minus $, RSP, parentheses, divide by 8, add 1. Maybe that's more reasonable. Somewhere else just getting the number 1. It says there's 7 quad words in the activation record. Let's actually, can we show it? No. I have to dereference a pointer. P/X, 7 of them. And we're showing them like this. G stands for quad word, $ RSP. And as confirmation, let's just check, say that W. P/X ampersand W. Where are you? You're at DEA0. DEA0. And sure enough, that's a -1. It's in the activation record of the called function. Okay, got it. Now that we could check D too. D has been computed back here. Let's just for the practice, we'll do that one too. P/X. What was that guy? It was D. Okay, ampersand D. DEA8. Hey, it's this guy over here. And it looks like a real mess, and it looks like it's negative. See the C in front? That's definitely the sign of a negative value. So how can we verify that? P/ in decimal D. Oh, wow. D really is negative. So if you're debugging it and you come to that mess up there, you can recognize you have a horrible negative number. Okay, there was something more here. We have 2 activation records, and this one, it has 7 quad words in it. What did the old one have? It had 21 quad words. Okay, we're going to put them side by side. 7 plus 21 is 28 quad words. So let's do it now. X/28. X quad words. $ RSP. Okay. Let's see. This is the newest quad word up here. In fact, we can confirm it. Here it is, and here it repeats itself. Same address. That's the newest quad word, and it goes for 7 of them. 1, 2, 3. First, look at the front end is on the boundary. We know that. And then there's 1, 2, 3, 4, 5, 6, 7, and this one ends. That's its back end. Okay. Now, did I say that right? That is, yeah, that is the back end. Okay. How can I? Okay, yeah, that's pretty good. This is front end, and then we go to the back end of that guy after 7 of them. Okay, and then we run into the front end of the previous activation record. And remember what I was telling you, when the call happens, there's a push RIP. It adds an extra one on there. And that's what you're looking at right here. That one is the extra piece pushed onto the old activation record when the function was called. If we scroll up here, watch up above, it ends here. It ends in E088. Here it is. Okay, that's the old front end of the old activation record. But when the call happened, this was pushed to it, and now we consider that to be, and it's off the boundary, by the way. That's the the back end of the old, no, it's the front end of the old activation record. I hope I get the language straight here. That's the front end of the old activation record. Here's where the front end used to be. But so what is that 6-digit number? That's the address of the instruction inside the caller function that will execute when control goes back to the caller. That's how it remembers it. It's tagged on at the end right there and makes the old activation record have a front end that's off the boundary so that the new one can start on the boundary over there. There's one other thing we got to, let's confirm this. And let's see, we want to just look at it directly. X, $, RIP. Okay. See, this is an instruction. They're always low numbers. 6 digits is very low compared to 16 digits, on other addresses. And that compares favorably with this one. It's not far apart. That's the address of the compiled code that will execute when return goes back to the caller. This is the compiled code this is the address of the instruction that will execute the next time I press the letter N. This is the one right now. There was one other thing, is that the back end of, okay, let's see if we can get this right. The address of the back end goes to the front end. I gotta say this right. The address of the back end. Okay, gotta find this for you. The address of the back end. This is the back end itself. This is its address. D7FF DF60. Now that becomes, and when you write assembly programming, the first thing you do is push RBP. That number that's highlighted is RBP for the old activation record, and it's going to get pushed as the first back end of the new one. What is it? It's DF60. But there it is. So that's the back end of the new one, and it's holding the address of the previous RBP. It's right there in plain view, and the machine is confirming the theory. Okay. All right, and then there's some local variables declared. There's some -1, and this was D, and we haven't had time to figure out what these others were. Those might be are those the values that were passed in? It gives it to us in decimal. I'll tell you what, we can have an answer in decimal. Let's do it. X/7 DG $, can't find you. No, it's not it. There it is. $, RSP. Okay. Didn't do any good, did it? That didn't tell us anything. Those are addresses, except I don't know why that's the W. Those are addresses up here of this. I can't explain it. Okay, all these strange numbers, whatever they are. Oh, as integers, aren't they? We wanted them as float numbers. Can we still do that? Yeah. Sorry, I think this comes back. The first one is 6.9. That's not one of our passed in numbers, is it? Passed in was 10, 12, and 13. 10.1, is that one of them? 10.1 is one of them. There's a NAND that's beyond infinity. We can't deal with that. Oh, No, that's pretty good actually. There's the first passed in number, or here's another one, and here's another one. And it's they're stored little Indian style. This one is actually first, but it's further down into the, and then this one, and this one. Okay, so that's really strange. I don't know what top of stack is doing, but inside the activation record of the new function, there are the three passed in values, here, here, and here. And he doesn't know what to do when you say show me 1111 as a float. It crashes out and says that I can't deal with that. But if you ask for it as an integer, then it's -1. Makes sense. Okay. And that's the value of D that was computed. And here it is. This is in IEEE down here. But if you just took the same bits and displayed it as 2's complement, you'd see that number. Okay. I think we'll continue and finish this off. Next, it's going to return D. You know, I didn't. Before we do that, we'll give it one other shot. How does it? One. Oh, I lost my place. Here it is. Let's check XMM0. See if it's going to put D into XMM0. That would be P/X $$ XMM0. Now, you remember from lectures long ago, the XMM registers have two numbers inside. Both are 64-bit floats. And I often call the first one the low end and the high end. The low end is on the right, according to Little Indian. So I have to pick one of two. And it looks like this: V2 underscore int 64-bit numbers. And between the two, the one on the far right is number 0. Well, that didn't help us at all. That's what it is. What would be? I hear. I lost something. The reason is returning D hasn't executed yet. When that executes, the D value will be copied into XMM0. I was hoping that it was already there, but it's not. So let's go ahead and execute return D. And has it really ended? Let's try that. XMM. What was D? D was oh, it was up here someplace. Here it is, -408. C is definitely negative. That might be it. 408, 68. It has evidence that is really negative, the returning value of D. Well, let's go one more. We're back in the calling program. And now you can check what is, might not be worth it. Well, I can't find it. We could output RSP has changed. P/X $RSP. This is the old RSP that belonged to the caller previously. And let's go ahead and let it finish. It outputted what it received. Why did it give us a -1? I don't know that one. It says the discriminant is this kind of number. That's pretty good. It says goodbye. That's when it returns 0. And now it stopped executing. And it's not running. Okay. So, any questions, people? we're going to come to a close with this. Okay, so let me see if they not there, not here, here. Okay, there's an hour preview, in hour and 10 minutes, the preview into the workings of GDB and programmers who are just frustrated at their program not producing correct results often fall back on GDB to find this horribly hidden bug. After a while, you just can't simply keep putting printf statements to watch your data. It's more practical to watch a register change its values step by step by running GDB. And you saw it here. And that's a preview of what it's like. We can go investigate every AR record. We can display the whole thing and look at it. You can actually make changes live, but that's a future lecture. We're just looking at data now, but it is possible to change the value of a variable, a C++ variable, and continue executing, or change the value of a register and continue executing. And you'll discover what your value should have been at that point. So it is a debugging tool. That's why it exists. Okay, are you okay, everyone? You got to wrap your brain around that. It ain't no easy walk in the snow. It's there's a walk there. We'll try something else here. So that this is in case you want to record it. You won't need this for the coming test, but you'll need it for the final. To look at an XMM register, the P is for, I think they took it from print, but it means output the value directly. And after the slash is the format. X would be for hex format. D is for base 10. T is fully binary. I'm thinking, are there any others I remember? I can't remember anymore. Okay. And then over here, if you're looking at a register, you have to use a $ prefix. If you're looking at a C++ variable, then you just name the variable directly. P/X count. And it will show you what your program variable name count holds at that moment. Because of the complexity of XMMs, there's actually two of them in two registers in under one name. And so you saw me in past weeks draw, sometimes I drew it and said, this is XMM4. There's an invisible line in the middle, and this is called the low end. And it's indexed as number 0. And this is high end, and it's indexed as number 1. And they speak of this as being an array of two components, not an array, a vector of two components. So you can see it essentially up here. This is a vector of two components. We're going to treat them as integers and show it in, what does the 64 mean? Show us 64 bits, and 0 is the low end of it. So you can see 64 here. If you want to split that in half, they have a means to do that. X, M, what is it? 8.v4 int 32 and then 32. And then in here, you can place a 0, a 1, a 2, or a 3, like 2. And now those would be 32-bit float numbers, the real C++ float word, not double. 0, 1, 2, 3. Each of those 32-bit float number in IEEE float type format, and you can look at them individually. So again, it's kind of implying this is a vector of 4 pieces. And if we're going to look at them in, see, over here it says PX. X is just says, give me the bits and in hex digits. That's why this int is here. And if you wanted it in float, you start out P/F. And I forgot what you do over here. It's float 32, I'm pretty sure. 32. And you pick one of the 4 components. 1. So it would be v4 dot xmm8. Okay. We can pick out anything we want in all those XMM registers by carefully appending this dot and a description of what we're looking for. All right. Everybody still here? Okay. Let's see. Next week, Thursday, there's a test. And you don't have to be here in California. You can be traveling in northern Japan or southern Indonesia. It doesn't matter. But what do you need? You need ability to receive email. Email. Okay. And one person has already written me and said he'll be in Northern Europe, close to the Arctic Circle, on the day of our test. Could he take it later? And I said, I emailed him back and simply said, make sure your hotel where you're staying will have a communication room where you can use a computer and receive email. You got to receive email. Okay. I don't care where you are. That's not important. Okay. So on that day, I'll email you your test around 2 p.m. 1:55 to 2 p.m. And I'll send it as .odt form. And I think I explained earlier, you may write directly on answers directly onto that form, under that format, or you can change it to DOCX form, and that's fine, but no other changes, only those 3. DT or DOC or DOCX. Okay. It's too hard for me to put your score onto it if it's a PDF form, because I have to drag out a different editor made this specifically for editing PDFs. I don't want to do that. Just these 3. Okay. Some questions are real easy. Who's the king of the assembly? Some are pretty hard, like convert a repeating IEEE number to decimal.
Professor, will there be any multiple choice?
I was just running over what to expect on next Thursday. Uh, between around 2 o'clock. And you don't have to talk to me on Zoom. You can do this whole thing by email. If you're traveling someplace, make sure that you can receive your mail. Then you can go offline if you want completely, and then come back and send it back to me at 4 o'clock, 4 p.m. return.
Will there be any multiple choice?
Conceivably, I haven't made it yet. That's my job for this weekend. Your best way to answer that is download last semester's midterm. And this semester's will be patterned on the same style. And I won't use the exact same questions, but a lot of them are very similar. If the question on the old one said, I'm going to numbers, convert 22 and 3/7 to IEEE. I don't have time to make up new numbers, so I'll just change the problem to be 27 and 9/11 to IEEE. The work is just about the same. The numbers are a little different to IEEE. Well, and if it says who is king of rock last semester, then this semester it will say who is queen of rock. No, it'll say who is Chris Sawyer. And so your best guideline is just the old test. There are 3 different ones. You get all 3 of them from last semester because there were 3 different sections. So everybody had a different test, and you can see some easy questions. You don't even have to look it up. And then there's some middle grade questions where you might have to look through your notes carefully. And then there's, I think the math is the harder questions. But that's just my opinion. Everybody with us in that? Okay, so where was I? We're back here. How to study? Well, math questions need practice, but the other kind of questions need organization of your notes. Practice, P-R-C-T-I-C-E. Okay, that's good for IEEE problems. But the rest of your questions are the kind where it pays to have your information organized. Organized means you can find stuff in it. If you videoed one of these lectures back at the beginning of February, and the answer you're looking for is in the 32nd minute of the video, you got to fast forward through that looking for the answer. That's not highly organized. So everybody organizes his information in a different way. I'm going to leave it to you to decide that. But here, you don't want to overrun your 2 hours looking for a trivial piece of information that should be easy to find. In fact, at that point, if you're watching a video to find your answer, it's probably faster to just ask Wikipedia what the answer is. Yeah, I think there comes a limit to how much time you can spend looking up stuff. So just because it's open note test doesn't mean no study. You should study your information, but more in the sense of how can I find it quickly? If I ask you to explain to me how Control D can get you out of a loop, can you go directly to a place where that's done, and then just explain to me from those notes? So there can be questions about programming but you don't write a program that executes. There can be questions about terminating a for loop with a control D. Explain how it works. Explain how to get the remainder when you divide one integer by another. You can look that up. It's got an easy answer, but it saves a lot of time if you know how to directly go there and see that problem solved already. And as last resort, go ask a web search, and they'll have an answer for you there. I think last semester students did that a lot, and it's okay. All right, so what can you do this weekend? Yeah, organize your notes, or whatever documents you keep. They can be electronic notes, it's okay. You should practice conversions so you don't lose time trying to figure out, what do I do next? Do I do consecutive divisions, or do I do consecutive multiplications by 2? What's the next step? How do I express the bias number in hex so I can save time on this subtraction? Practice math, I'll call it. All that stuff. And then famous facts. You should know where to go directly to find what is the value of infinity. Infinity. That's a famous fact. Can you give me infinity in hex? Can you give me infinity in decimal? Can you? What's the smallest normal number possible in either format? So those are fixed facts, I would call them. What professor screwed up his teaching of operating systems so badly that it resulted in Linux? You can Google for that name. When Linus was a computer science major in Helsinki, and the instructor did it such a horrible job in the operating system class that he took the winter break off, and that spring semester to create the first version of Linux 1.0. See how that happened? Now, some screw up professor made it so bad that it caused the creation of Linux. And that's what I teach from. That's what you're using in some form or another. Okay. Who was that famous professor? See, that's culture. It's the culture of the workplace where you're going to make your big dollars someday. It's how we all got here. It's current science stands on the work made by great giants of the past, and there are only 3 operating systems. Isn't that true? In the whole world. And there's there's the Microsoft operating system, there's the Linux operating system, and then there's the Mac BSD that Mac borrowed it from the original Unix. Cost money, but it became free open source under the name BSD, and that went into Macs for years and years and years. They used that one. Okay, so I think there's only 3 operating systems in current use, but they have a lot of flavors. There's 100 different Linuxes with painted desktops that look pretty in different ways, and some have flowers around the edge, and some have bird hawks flying in the desktop. But inside, there's only one kernel. There's 3 of these kernels in the world. That's all you get. Okay, that's culture. Okay, so Sometimes your job interviewer will ask you a cultural question, but most frequently they ask you tech questions. Any questions, folks? We're ending today. I don't have any more notes to tell you about. Come back on. I didn't put that message in the chat. You have the references where to get help, I assume. Let's do that as one last thing. Where's my file folder? I'm looking here it is. Okay, let's do this. Control A, C, and where is the chat messages? Huh, can't find it. We'll get this right. Chat messages. Okay. I'm sending you a long chat message, but it's stuff you already know. You keep it on hand for emergencies. Control V. Okay. Control Enter. So if you're programming this weekend, email one of those two TAs at the top of the message and try and get some help. They're pretty good at it. They respond, both of them are pretty good at responding as soon as they see your message. Trouble is they have to live too and do stuff to stay alive. So, but both of them I found very good. Johnson and Daniel I know very well. Sam I know partially well, and he's okay. He's a good guy too. And if you have administrative issues, you can email me. And I don't have, on weekends especially, I don't have instant turnaround time, but usually a day or so, I can act on your needs for administrative issues. Okay, and if you want to remove your hold, there's how you can do it easily. Okay, any questions, anybody? We're going to end here. What is infinity in base 10? Does everybody remember that? I think you know. What happened here? My things are in the way here. Okay, wait a second. For some reason my chat messages disappear, but it doesn't hurt anything. Okay, class, I'm going to I'll just be here, fulfill my duty to be here till 4 o'clock. You got any questions about how to study next week, this weekend? I'll be glad to chat with you. So have a good weekend. Stay in tune. Finish program number 3 if you haven't done that already. Actually, you don't need programming till the week after we come back. So that's not the big issue. The big issue is to study these other subjects until then. Okay. All right. Okay. Take care. Goodbye, Serafina. And goodbye, Nick. And Joseph. All of you have a good weekend. I want to get you passed out of this class. You sure want to visit me again. This gets you employed. You're welcome, Z Wang. And Joseph, you're welcome. And let's see, how do I get this off of here? Okay, so let's see.